Hi everyone, let's look into question number 4B of elementary structural analysis from the examination held on May 2014. I feel like some information was missing from the question. It should have given us the location of joint U2, and I have assumed it is situated in the mid portion of the bottom members. So the total distance it calculates out to be 16 meters. Therefore, distance of U2 from joint L1 should be 8 meter. That's our assumption. And with that assumption, we can start our modeling. I have loaded a STAAD profile in metric units. So let's enter the joint coordinate. L1, we would assume that it is at the origin 0, 0, 0, L2 6.25000, and L3 that should be 6.25 plus 3.5, which is equal to 9.75, and L4 it is 16 meter far from the origin. For joint U1 and U2, we will just create a perpendicular member starting from L2 and L3 respectively, and our U2 its coordinate would be 8 meter in the X direction and 6 meter in the Y direction. So that's 8 meter in the X direction and 6 meter in the Y direction. So I will quickly load the front view of this structure, and I will enable our node numbers and beam numbers. That will make our life easier. So let's input the node numbers for creating the lines for our truss. 1 will be connected to 2, 2 will be connected to 3, 3 will be connected to 4, 1 will be connected to 5, and 5 will be connected to 4. And then 2 will be connected to 5, 3 will be connected to 5. And then a line from 2 to 4 and 3 to 5, it can be drawn by selecting create beam by perpendicular intersection. Click join 2 and click anywhere. It will create a perpendicular member. Click the joint, click anywhere in this beam, and it will create our model. Then go to properties, create a prismatic section. I would just assume it is 0.4 meter by 0.2 meter concrete section. It won't matter for determining the member forces. Just click add, close, and then click assign to view, assign. Okay, then go to specification. We need to specify these members belong to truss structure, which means we need to release moment from the end point of the members. For doing that, click beam, go to truss, and click add, and then click assign to view, assign. Okay, and then go to supports, create supports. We do have one pin support, add, and we also will create a roller support using fixed butt option, and we will be releasing in all the direction except FY. Select support 2 and then select the node, click assign. Okay, select the roller support, select the node, click assign. Okay, go to loading, go to load case detail, click add, select dead load, click add, and close. It will create a load case for us. Then select the load case, select add, and then we'll define our nodal loads. There are two ways in which we can apply the load. One is to resolve the forces manually and then apply the load in X and Y direction. For example, for this 30 kilonewton load, let us consider a horizontal axis and let this angle be theta. So tan theta would be 4 by 3, cos theta would be 3 by 5, and sin theta would be 4 by 5. Then the vertical component of this force would be 30 sin theta, which is equal to 30 multiplied by 4 by 5. So 5 on the 5, 5 6 are 30. This should be equal to 24 kilonewton. So we can apply a vertical load of 24 kilonewton at U2, and the horizontal component should be equal to 30 cos theta, which should be equal to 30 multiplied by 3 by 5. This should be equal to 18. So at U2, we can apply 18 kilonewton in horizontal direction and 24 kilonewton in vertical direction. Similarly, we can resolve a 60 kilonewton force into horizontal direction and vertical direction, and it can be applied at node U1, and we can do the same for this 30 kilonewton load as well. The other way is to apply the inclined load directly on a STAAD Pro, but for using that, we need to understand the concept of a line of action of the force. Just guess how many points do we need to make a line? That's two, right? So that's the same number of the points that is required to define line of action of a force. So in STAT Pro, one of those 2 points is already fixed. Point is the node itself, and we will need to find out another point that's on the line of action of the force. So we will use the geometry to find the other point. For example, for the 30 kilonewton load, its slope is 4 vertical to 3 horizontal, which means if we travel 4 meter downward over here in vertical direction, then we need to travel 3 meter in horizontal direction. So that will be the coordinate of this point, right? So we have one point, the node itself, and another point which is at 4 meter in the vertical direction, 3 meter in the horizontal direction. Our line of action is fixed. Similarly, since all of the forces are inclined at same angle, we can say if we travel 4 meter on the downward direction, then we need to travel 3 meter on the horizontal direction. So that's all we need. So in STAAD Pro, to define the inclined load, just enter the magnitude of the load in x direction. For example, for 30 kilonewton load, I'll type 30, check inclined load, and I'll go with a relative. X would be 3 and Y would be -4. Add, and for the 60 kilonewton, just type 60 over here and click on add, close, and apply the 30 kilonewton load to node number 1 and node number 5. 1 and 5 assign, and similarly assign 60 kilonewton load to node number 6. You can see that line of action of 60 kilonewton force goes through node number 2. So there is another way we can apply this inclined load. I'll just show you quickly how we can do that. I'll just edit this load just to make sure we are coming into the same conclusion. Since we have already the coordinates of 2, click on reference node, click on node number 2 and click on modify. So there was no change in the load direction, which means we can use either of the approach. I would suggest using the reference node whenever the load is passing through a specific node, because we don't need to do a bunch of calculation for that. But we can't apply same principle for node number 5 because it goes like somewhere in between the member 3, and we don't have a node over there, and same case applies in node number 1 also. So that's the difference between the reference node and relative coordinate. The absolute system is also more or less similar to reference node, but here what we do is we specify the global coordinate of the point. In relative, we use the distance between the known point and unknown point, but in absolute, we need to type the global coordinate of the new unknown point. So that's the difference. I'll just leave it with reference node, modify, close, and then go to analysis, define command, add, close, and then click run, click save, and it will open the post-processing window. We have got few more warnings, but they are normal in a Truss structure. Go to post-processing mode, done, select your load cases, apply, okay. If you want to check your reactions, you can go in the reactions, and we have -72 kilonewton reaction in horizontal direction, 58.5 kilonewton in vertical direction at node number 1, while we have 37.5 kilonewton reaction in vertical direction at node number 4. For beam results, we won't have any moments in the z direction, neither on the y direction and neither on the x direction. Similarly, we won't have any force on the y direction and any force on the z direction. All we will have is axial forces only. And if you want to clear out your diagram, just go to scale loads and result, click here outline and just make sure this button is checked over here for the color coding for the axial forces. Then click apply. It won't give you any number, but the green represents the compression and red represents the tension. And then you can click annotate beam results, axial ins, annotate and close. So those are the numbers that you want. And if you want to clear out your diagrams, just remove your labels for the node numbers and for the beam numbers. Apply and OK. So the question asked us to calculate the force in L1 U1. So L1 U1, it would be 57.5 kilonewton in compression. L1 L2, it would be 100 kilonewton in tension. L2 U2, it would be 50 kilonewton in tension again. So that's all for today. Thank you, everyone. Have a good day.